I'm going to introduce this material to you. I think it's going to be a little bit simpler the way I introduce it than it's presented in the lectures. But then I think the lecture's going to fill in a lot of this information for you. Okay, so I have a bunch of files here. I numbered them 1, 1A, 2 in the order that I expected to, talk about them. Okay, so I'm going to open up this first one that you might want to follow along with called chi-square.pdf. And I'm actually not going to open it. Actually, let me open it so you can see what it is. Okay, chi-square, here we go. Okay, it's basically a PDF of a PowerPoint that goes through an exercise involving the calculation of something that we're about to call chi-square. So now you have that to follow me with, and I'm going to kind of step through this manually so you can see where a lot of this stuff is coming from, I hope. Okay, so I hope that this works out better than just popping through this as I printed it out so I would have a reference for this. Okay, so I'm going to start off with a random sample of 200 patients, right? My sample size is 200. I have 200 patients I randomly sampled that take part in a community healthcare are in a community healthcare facility, and we test them for HIV, and we find that 40 of the patients are HIV positive. Okay, just a quick question: what's the prevalence? If this sample is a good random sample, what does it look like the prevalence of HIV is in this population? Right? Prevalence is going to be 40 over 200, right? Right, which is 20%, right? 20% or 0.20. Okay, so now I also, I said to myself, what, 20% of the people in this population are HIV positive. That's a high rate. It's maybe a clinic that serves people that are likely to be HIV positive. Perhaps many of them are drug users, right? Maybe that's why this population has such a high prevalence. Okay, well, in fact, let's take a look at that. Let's go back and examine these 200 people, except I'm going to break this up into a table, right? Remember we made that table with the diagnostic tests, a row and a column, right? I'm going to do the same thing now with the diagnosis of HIV positive and whether a person is a drug user. And when I do this, I like to organize this the same way every time I do this, just to make it, I don't have to do it this way, but just to make it easier for me to evaluate as I go through this. I like to make the rows, the exposure, right? The thing I think is causing an increase or a decrease in what I'm looking for, the disease, and the vertical columns, I'm going to call that the disease, right? In other words, HIV positive or HIV negative, right? And exposure is drug user or not a drug user, right? Bottom row is not a drug user, top row is a drug user. The first column is HIV positive, the second column is HIV negative. Okay, so let's take a look at this. Now, my expectation is before I even do this, I may say to myself, I just said to myself, I have 200 people here total. Of those 200 people, right? Of those 200 people, how many of them are HIV positive? Well, I said 40 were, right? And how many of them were HIV negative? That leaves 160, right? So this really is my prevalence down here. So I know in this column, it's going to add up to 40 because I know starting off out of the 200 people, right? Now, if I go back and I resurvey these people to find out if they're IV drug users, right? Well, what's my expectation here? Well, my expectation is that there's no difference between the rate of whether a person's HIV positive between drug users and non-drug users. So if I'm looking at that, well, let's see. Let's say that I find out that there are what number did I give it? Let's say I find out there's 50 drug users and there's 150 non-drug users. Right? I go back, survey all these people. 50 of them turn out to be drug users. 150 of them are not drug users. So now, before I actually make counts of people, are you this and this, or this or this? Before I do that, I'm going to evaluate this for myself. If 50 people turn out to be drug users, and there's no difference between drug users and non-drug users with respect to whether or not they're likely to be HIV positive, okay? If there's no association between drug use and HIV, well, then how many of the 50 would I expect to be HIV positive? I expect the same as the prevalent of the general population, which is 20%. What's 20% of 50? 10, right? And that would leave 40 that of those 50 people that are not HIV positive. Well, how about the non-drug users? Same thing. I would expect to get 20 if there's no association between drug use, intravenous drug use, and being HIV positive. I would expect 20% of these people, so that would be 30, and that would leave 120 that are not. Okay, that's the way I would expect this table to look. Okay, now we got a name for this table. Anybody been reading ahead and know what the name for this table is? You'll hear it called two things. One, sometimes you'll call crosstabs, and a lot of times you'll hear it called contingency tables. Right? So, anybody have an idea? Or a 2x2 table? That's good enough too. All right. So we have this 2x2 contingency table, right? And this is what we would expect the outcome to be. So I'm actually going to call this, right? If I could get up there again and not smear all this stuff over here, I would write up here expected values. That's what I would expect to be the result if I took this survey and went back and checked to see who was an IV drug user and who wasn't an IV drug user. Well, now I'm going to make a new version of this table down here. Right? Okay, and we know that out of these 200 people, we already know that 40 of them were HIV positive, 160 of them were not HIV positive. And this is drug users, this is non-drug users, this is HIV positive, this is HIV negative. Okay, now I'm going to go back and actually look at these 40 people that were HIV positive and actually ask them, have you used intravenous drugs? So as it turns out, I find, I'm looking at the papers here because I want to do it exactly the same way I do it, that I've done it on this PowerPoint, so that if you go back again and look at it, it'll make sense to you. Okay, so as it turns out, I find that 15 of the people that were HIV positive were intravenous drug users, and that leaves 25 that were not intravenous drug users. Okay, now similarly, let's see, well, what about the 160? Well, the 160, that's going to leave 35. Let's see, let's say that winds up being 35 that are HIV negative, and 125, because we still have 160 people in this study that are HIV negative, and 125 are HIV negative. Okay, so how many drug users we have? We have 50. How many non-drug users? We have 150. So it's the same table as we have up there, except this represents the real world distribution. This is what we would have expected if drug users and non-drug users had the same rate of HIV diagnosis. Okay, and this is what we find in the real world. Okay, in our sample, in our real world sample. So instead of expected values, I'm going to call this table down here observed values. Okay, so now let me ask you this. In a perfect world, if there's no association between intravenous drug use and HIV status, in a perfect world, there's no association, there's no risk from HIV drug use. What would you expect the difference between what's in all of these boxes be in the expected values and in the observed values? You'd expect them to be the same. You'd expect your observed values to be the same as what you expected. In other words, if I looked at intravenous drug users out of 200, out of the 40 people that are HIV positive, I expect 10 of them to be drug users and 30 of them not to be drug users. And when I go to look at the observed values, I would expect 10 and 30 if there's no association. If there is an association, then I would expect to see that intravenous drug users might be more likely, or more of the intravenous drug users would have HIV than I expected, based on the population prevalence. Okay, so the difference between what's in these boxes, in a perfect world, if there's no association between these two variables, I would expect them to be the same. Okay, so I'm going to add up all the differences. I'm going to take all these differences. Okay, in a perfect world, let's imagine that this box and this box are the same. I'd have 10 here and 10 here. I'm going to add up. Okay, sigma is capital sigma is a Greek letter representing total, as we used it before, for various things, for some of the mean as squares and so on and so forth. So I'm going to take the sum of all these, the sum of 10 versus 10, 10 minus 10. The difference is 0. Difference here is, in a perfect world, distance there would be 0. The difference there would be 0. The difference there would be 0. So the sum of all these differences would be 0. The stronger the association between HIV drug use and whether a person is HIV positive, the bigger the differences I would expect from the expected values. Like I might have expected, maybe, I would have gotten a situation where all 40 people would have been 40 and 0. All 40 people that were HIV positive were drug users, right? Now, this doesn't show quite that strong an association, but there is something that's different about this observed values versus the expected values. So I'm going to say, okay, let's add up all these differences. I'm going to take the sum and the bigger the differences are, the more likely it seems that I would have an association between drug use and HIV status. Everybody get why I'm saying that? In other words, the bigger the differences between the expected values and what I actually observed, the more likely it is that IV drug use has something to do with being HIV positive. There's an association. Are you comfortable with that?
When you sum it, do you always take the positive?
No, actually I'm going to do exactly the opposite.
Oh.
I'm going to say 10 minus 15 is minus 5. And then I'm going to add, let's see, 30 minus 25 is plus 5. Then 40 minus 35 is plus 5. And 120 minus 125 is minus 5. And what does that add up to? 0. Now, what did we do when we were finding some of the differences between the means and each individual values, the differences? We squared it. I'm going to do exactly the same thing now. I'm going to say I'm going to square each one of the differences. 10 minus 5 is 15, squared minus 5 is minus 5, squared is plus 25, right? And 30 minus 25 is plus 5, squared is plus 25, and 40 minus 35 is minus 5 is going to be plus 25, and again squared is 120 minus 125 is minus 5 squared is plus 25. So when I add all those up, it's equal to 100, right? Well, remember what we did with the sum of squares, right? We squared all of the differences, right? So that we would have all positive numbers. We add them up, it gave us the sum of the squares of the differences. But now we had to bring it back into the range of numbers, which represented a real variability. What did we do? We divided by something, right? Right. By the same. Well, now hang on a second. We actually took right n minus 1, and then we took the square root also, right? Remember, because we went from variance to standard deviation, we also took the square root. Well, in this case, what I'm going to do is I'm going to take the sum of all the squares of the observed values. I actually usually do it the other direction. It doesn't really matter because the signs will come out. Usually I'm going to put the formula up here. I'm going to take the sum of the observed values squared, observed values minus the expected values squared, over, and I'm going to divide it by the expected values. Okay, and that'll bring the numbers back down to the range that we would expect to be working in. Okay, so now if I do that here, that's going to be the sum of all of those observed minus expected values squared. is going to be 100 divided by, well, actually, I'm going to have to do it for each one individually, right? So let's do that up here. Let me go up here and undo that. Control 6. I got a little bit of room left to work with. I'm trying to stay on one page. For some reason, it doesn't like undoing. Okay, I have to live with that. Okay, so maybe I'll open a new page. How's that? So I can have something here. Okay, so I'm going to do this on a new page here. Nope, wrong one. There it is. Okay. Okay, so let me get this out of the way. Okay, I'm going to come in here and work on this. So I'm going to take the sum of the observed values minus the expected values squared over the expected values. Okay, so now actually this is a sum of each one of these analyses. So it's going to be the sum of, I'm going to add up. Well, the first case, the observed values, the observed value was 10. It was 15 minus 10 is 5. Squared is 25 over the expected value. What was the expected value? Was 10. Right? 25 over 10. Plus, the observed value was, actually, did I do that? No, the observed, I'm sorry. Yeah, I got it right. The observed value is 25 minus the expected value is 30. That squared is going to be 25 again, right? A positive 25 over the expected value, which was 30, right? Plus, I'm going to move down here so I don't have to move the page. The next cell is going to be the observed value is 35 minus 40 is minus 5. So observed minus expected is minus 5 squared is 25 again, divided by the expected value, which was 35. Excuse me, which was 30. Excuse me, which was 40. Thanks. Confusing myself. I got so much stuff on this page now. Okay, and finally, the last cell, the expected value was the observed value was 125 minus 120 is 5 squared is 25 divided by the expected value, which was 120. Excuse me, which was 120. Yes. Am I right about that? Yes, I am. 120. Okay, so let's figure all this out. So the sum of all of these is 2.5 plus 25 over 30 is how much? 25 over 30. 8.3, excuse me. Yeah, 0.83. 0.83. 0.83. 83 plus 25 over 40. Which is 0.625. I'm going to call that 0.63 plus 25 over 120. 0.02. 0.208. 0.2. I'll just go 0.21. Okay, so let's add those up. The sum of all these is equal to, I should have done it. At the same time, I should have been just plugging it into clear here, clear there. 2.5 plus 0.83 plus 0.63 plus 4.1. I'm going to take your word for it because I don't want to start again. Calculators on computers are really cumbersome. So the sum of all this is equal to 4.1. Okay, so now we have to make a judgment now. Is that difference big enough for us to say that there really is an association between HIV status and IV drug use in this study. We know in the real, let's forget the real world. We know there is, right? But in this study, is that big enough difference? Remember, the bigger the difference is, the more the bigger the larger the difference in the rate of HIV among drug users, right? So the bigger that difference is, the more evidence that I have that there's an association between that exposure and that outcome. Okay, so now, but is 4.1 big enough? Okay, well, let's think about this for a second. Should I expect it to be zero ever? Well, how often would it be zero? If we really did this study and there was no association, how lucky would we have to be to get exactly what we expected and not one person off or two people off or something like that? It would be unusual for us to, so I can't just say different from zero is enough for the sum of all these differences, right? It's got to be a certain size. In fact, there is a probability distribution called the chi-square distribution. It actually has many forms. I think that if you go to, it looks something like this. Let me draw it on here first. I'm going to hold on to that 4.1 for now. I'm going to go over here and I'm going to draw it for you. Okay, and I'm going to reason out what it might look like in a reasonable world. So first of all, well, I wouldn't expect a normal distribution because the lowest value, this can't, based on the fact we're squaring these numbers, it can't have a negative value, right? The lowest it could be is zero. So there is no anything below zero, right? So what would I expect the most likely outcome to be? Well, zero might come up occasionally, but not that often. Really, the most likely outcome is that I might expect a number a little bit above zero is the most likely outcome. And for zero probably is pretty unlikely outcome. Just like it's not likely that you're going to get exactly 50 heads if you flip 100 coins, right? So I'm going to say, gee, I'm going to start off a little bit lower and then go up. And then as we get past the number one or so, I'm going to say, okay, it goes up, the probability goes up. But now as I start to get bigger, as I start to get a bigger difference for my chi-square value, that value for the sum of all those differences, right? The probability goes down. And I'll bet you just like the normal distribution, it's asymptotic. It never really gets to zero, but it gets lower and lower and lower. So in order for me to say that this difference is big enough, right? I want to see a value that's so far out on this distribution that the probability of getting that big a difference, if there's no association between the two variables, is less than, what do you think that area has to be? Less than what percent? Bingo, 5%, right? We want to get far enough out that's less than 5%. Well, we got a problem here. I just gave you a 2x2 table. We could do the same thing. Let's say that that we instead looked at somebody that never used IV drugs, somebody that only used it a few times, and people that use IV drugs regularly. Now we got 3 categories of exposure, 2 categories of outcome, HIV positive or negative. Now we have a 3x2 table with 6 boxes. So just the fact that it's got 6 boxes makes it a larger number. So I can't use the same distribution. This is the right one for n is equal to 4 boxes, right? 2x2 table. For a 3x2 table with 6 boxes, we're going to need a different one. Might look something like this, where it goes for, that number has to be even bigger. It goes further out. That number has to be bigger to get to the point where that percentage is 5%. So what do we need? We need something that gives us the value that for our particular table, 2x2 table, the value that we can say represents less than 5% chance of being wrong if we say there's an association between those two variables. I'm going to step back for a second. I'm going to say H null and H alt. I'm going to throw in that a kind of like annoying thing that we do in statistics, and which is set up a hypothesis, which normally I would have done at the beginning, right? But I want to introduce you to this idea of how this works. Okay, H null is that there's no association. I'm not going to bother to try and figure fancy way to display it using Greek letters or something like that. There's no association between these two variables. H alt is that there is an association. So I need to know what number that chi-square has to be in order for me. A chi-square is represented by chi is kind of like a capital X as a Greek letter, right? So I want to know what number does chi-square have to be in order for me to know that there's only less than 5% chance I would get that big an outcome, that big a difference between the expected and the observed values, even if there were no association. It has to be less than 5% chance of that happening. How big does that chi-square have to be? What do you think we call that value of chi-square? Think back, what do we call the value of t that we had to exceed? We called it what value? The critical value. Exactly. We need to know the critical value of chi-square, and there's a different critical value for a different number of boxes in these tables. Okay, so let's take a look and I think we have it in here under formulas and reference. Let's see, do I have chi-square formula? I got the chi-square formula. Okay, and chi-square distribution. Oh, here's a number of different chi-square distributions based on the number of boxes and so on and so forth. Okay, but let's not worry about that. Let me actually see if I can't find, where do I have it? Okay, I'm going to look it up on here. Chi-square. Let's see. Chi-square. What? How about table? Okay, chi-square table. Here we go. There we go. There it is. Okay, let's take a look at the chi-square table. Okay, degrees of freedom. Well, how do we figure out what the degrees of freedom are here? We have two variables, right? We have two values for HIV status. We have two values for the exposure, right? So just like we did before, we're going to take each one and we're going to subtract one, okay? So the degrees of freedom we have in the rows is 2 minus 1 is 1. The degrees of freedom that we have from the columns is 2 minus 1. So we have 1 and 1, and we're going to multiply the two of them. So 1 times 1 is 1. In a 2 by 2 table, we have 1 degree of freedom. If we had a 3 by 2 table, like I described before, right, how many degrees of freedom would that be? 3 minus 1 is 2. 2 minus 1 is 1. 2 times 1, 2 degrees of freedom for that table. Okay, so 2 degrees of freedom. What does the probability of exceeding the critical value, if there's no difference, if there's no association, is 5% when you have a chi-square value of 3.841. Anybody remember what our chi-square value was that we calculated for? 4.1. So our value for chi-square for the distribution we just looked at, the contingency table we just looked at, is larger than our critical value for chi-square for that 2 by 2 for a 2 by 2 table. So that tells us the probability of getting that big a number, 4.1, is less than 5% chance if there's no association between IV drug use and no IV drug use. So that means we can do what to the null hypothesis? Reject the null hypothesis, accept the alternative hypothesis that there is an association, right? So how cool is that? I mean, now you have a tool that you could use on basically any categorical data. Now, out of those 180 variables that you have in the community health survey, easily 150 of them or more are categorical variables. Here's a tool that you can use to evaluate this. Now, we're going to take a look at this from another perspective also, which you'll see used in many, many, many studies, okay? Because a lot of studies are looking for exactly this kind of stuff. If a kid lives in the inner city, if a kid in the inner city in Cleveland, right, drinks water, drinks a lot of water, or doesn't drink any water at all, drinks other stuff and stuff like that. Either drinks water or doesn't use the water, drinks bottled water or something like that. Well, what is the likelihood that they would be lead poisoned, that they're above the threshold the action level for lead. I think it's nowadays. I think it's like 5 or 10 parts per micrograms per deciliter, right, of blood, right? So what's the likelihood they be? So they're either above the action level or not above the action level, right? Two categorical variable, two values, and they either drink the water or they don't drink the water, right? Or they're in an area outside of the area that's served by that water supply or inside the area, right? Categorical variable, two possibilities. You can set up a 2 by 2 table like this. And then you could say, gee, I think that I can reject my null hypothesis. There's no association between children being lead poisoned and drinking the water in the inner city in Cleveland because of that issue they had with their water supply. Okay, so you could do that. The only problem with that is that fine, you reject the null hypothesis, right? But it really doesn't, I suppose you could come up with the chi-square table doesn't give you a p-value. It just tells you, the probability is less than 5%, right, that you would get that outcome. But it doesn't tell you the probability is exactly 0.1% or 0.001% or something like that. It just gives you the kind of like a pass or fail kind of outcome. It would be really nice to be able to quantify these relationships. Okay, and I'm going to go back to that table again, especially the observed values. Actually, let me see, did I use a different table now?